Hey there, Mr. Sutton here, bringing you the BC Calculus 8-4 Part 2 homework solutions on vector free response practice. On this free response problem, which is calculator-based, we've got the figure above showing the path traveled by a roller coaster from time 0 to 18, and the position of the car in terms of t is modeled by these parametric functions. The velocity, the derivatives of these functions, although they don't call it velocity, we've got these functions here. So there's a bunch of things I'm going to be doing. I'm going to go ahead right away and just enter all of these in my y equals on my calculator. So there we go. Everything's been entered in my y equals. Let me go ahead now and actually do the problem. So we want the slope of the path at time 2. So to get slope parametrically, I need to do y prime of the input over x prime. So slope evaluated to, we've got y prime of 2 over x prime of 2, which I can do directly on the calculator. To do this on the calculator, I do a little fancy fraction here, and then I've got y4, because that's where I stored y prime of 2. y3 is really x prime of 2, and just press enter. 1.794, and let's see here. Yep, there it is. For this part of the problem, they want the acceleration vector of the car at the time when the horizontal position is x equals 140. So I have to start by finding t, and then I can take the derivative of these derivatives at whatever that time is. So let me start by setting my x of t equal to 140, and I'm going to solve this on the calculator now. To do this, I need to pay a visit to my y equals. For one thing, I don't want to graph all of these functions. I just want to graph x of t. So this first one I'm going to keep selected, but these other three I'm going to deselect so that I don't have to look at their graphs. And I also need to graph 140 because I'm going to see where this intersects with the graph of x of t. I also need to select a window. So for my window, I'm going to use 0 to 18 because nothing else really matters in terms of x values. So I've got 0 already in there and then 18. And let me zoom fit these to see if I can see that intersection between these. And hopefully there's only one intersection. So there's the x of t, there's 140. Let me do second trace, option 5. Enter, enter, enter. And we get an intersection point of about 13.6471 and some change. So there it is again. I'm going to store this as A on the paper and on my calculator so I don't have to keep referring back to it. So there's the approximate value of A. Let me go to the calculator now and let me just quit out of the graph. We're going to do store and then alpha A. Done. Okay. So at this point, we need to find the acceleration vector of the car at this time. So what we're going to do is we're going to take this A value and plug it into the derivative of x prime and the derivative of y prime. These are initially velocity components, so taking one more derivative gives me the acceleration. So the way I'm writing this is acceleration of A equals x double prime of A comma y double prime of A. So I'm telling people what I'm about to do, and now that I've said this, I'm allowed to just go ahead and take the derivative of these functions at A on the calculator. Now the nice thing is I don't have to actually tell them what x double prime looks like algebraically. Since I'm just doing it at a single spot, I can get away with just writing this without showing the function. So let's go ahead and do that now. So here's what x double prime of A looks like on my calculator. I did math 8 to get my derivative. X prime is stored as y3, so I need to take the derivative of that. And then alpha A to get my x equals here, and press enter. Comes out to about negative 3.529. So that's the x part of our acceleration. Now for the y part, going back to the calculator, I have pretty much everything I need with what I just entered up there. So I'm going to arrow up and grab that input again. But there's only one thing I need to change. I have to arrow over to my y3 in here, and I need to change that to, let's see, alpha trace. I want y4 because I need to take the derivative of y prime for this part. And then just press enter, and we get about 1.226. For this next one, we want to find the time at which the car is at its maximum height, and then find the speed in meters per second of the car at this time. Well, if I want max height, I need to know where the up-down derivative, the y prime, equals 0. I need to know those critical values. I'm also going to need to test the endpoints of this interval, 0 and 18, at least if there's multiple critical values in here. So we have y prime of t equals 0. That's my starting point. Let me graph that. So going back to the y equals, I'm no longer interested in x of t like I was on the last problem part. I want y prime of t. That was stored in y4. So let me select that. Let me deselect that other random thing that was in there. And let me see here. I'm still going from 0 to 18. But what else do I need here? I just need to know where this crosses the x-axis. So let me just zoom 0 that, because I've already got the interval from 0 to 18 entered in my window. So here is y prime of t. Once, twice, 3, 4, 5, 6. Well, just 5. So 5 different critical values that we may potentially have to test. What a mess. So to make my life a little bit easier, so here's the graph again. The good news is I actually only need to test out the local maxes if I'm looking for the absolute max. So I'm going to word this as follows. Y prime of t changes positive to negative at the following values. Now each of these values I'm going to find with an intersection, so I'm going to find this spot intersect with the y-axis, so zeros. I'm going to find this spot right here, this spot, and this spot, and I'm going to represent them as B, C, and D, so I can refer back to them quickly on paper and in my calculator. I'm only going to have to find the local maxes. So let me go to my calculator now and figure out where those are. So let me see here. Let's do second trace, and I've got 0, so option 2. And then let me just go all the way back to the beginning here. Woo! It's like riding a roller coaster, just like the problem. All right, so we go enter once to the left of that local max, once to the right, one more time for fun, and that's about 3.0239. So I'm going to store that value as B on the calculator, which I have to quit out and do immediately. So stow alpha B. All right. Let me find my next max. Second trace, zeros. And let me move my roller coaster a little bit further along. So we've got a little bit to the left of this local max, a little bit to the right. Enter again. And now we've got a 0 of 9.2394, which I will store as C on paper and in my calculator. So quit out of here. Let's see, store alpha C. All right, back to the graph. This is kind of fun. Second trace and zeros. Ride the roller coaster one more time. We just have one more local max to figure out the t value for, and that's right here. And enter again. So that's about 15.2896. There we go. And storing that. So stow alpha D. All right, we've got them all stored in here. Now, out of all of these, most likely this first local max is going to give you a higher height than the rest of these because you're going up a whole bunch because you have this positive derivative here. Then you kind of offset that, decreasing your height, and then you don't go up as much for the rest of this. But you can't say that and be rigorous about it and prove anything. So that's why we have to test all these points with our candidates test. So at this point, we're going to go through and test out these 3 local maxes along with the endpoints 0 and 18. So let's start with y of 0. So we're going to do this on the calculator now. To do this on the calculator, I conveniently stored y as y2. So alpha trace y2. And let's see, open a parentheses, plug in 0. There we go. Enter. Comes out to 0. Okay, well, that was kind of anticlimactic. Let's plug in B and see what happens there. So going back to the calculator, I'm going to snag my input from before. And in here, I'm just putting alpha B. Comes out to about 33.8348. Well, so far, that's the local max, or the absolute max. Let's plug in C now. Back on the calculator. Now instead of alpha B, let me go back in here, and I've got alpha C. Enter. That's 21.337. So not the absolute max. So still B is winning. Now we do y of d. So let's see, back up here, grab that. And in here we've got now alpha d. Comes out to 9.0146. So that's not going to win either. B is still in the lead. And finally, we're going to plug in 18. And again, we kind of expected this just because of how a roller coaster works. But to prove it, we need all these tests. So let's go back one more time, and now we're going to plug in 18 and press enter. That's a very low height, 0.6794. So this means, by the candidates test here, that our max height happens at t equals 33.8348 seconds. Or B, because that's what we represented as B. And actually, I take back what I just said. This is the actual height here in meters, not the seconds. The seconds was 3.0239. There we go. Well, it's a good thing I stored that as B and wrote B down here, right? Okay. So what are we going to do with this now? Because they had one more thing they wanted on this problem. They wanted us to find the speed in meters per second of the car at this time. We found the time, we put the units, now we need the speed. So for speed, we need to take the square root of the component forms for velocity squared and added together. So basically, we need x prime of b squared plus y prime of b squared, all of that square rooted. All right, one more trip to the calculator. So here's what that looks like on the calculator. X prime again was y3, so that's y3 of b squared. Y prime was y4, so y4 of b squared. Enter, grand total of, we're going 6.028, and that's going to be meters per second. For this last part of this roller coaster problem, they're telling us between 0 and 18 there are 2 times when the car is at ground level, in other words, y equals 0. We have to find these 2 times and write an expression for the average speed in meters per second of the car between these 2 times. And we don't have to evaluate it at least, but we do have to find the 2 times and set up something. So let's go to the calculator again. So I'm back in my y equals, and this time around I need to graph y of t, because I'm looking to see where y of t is 0. So let me go ahead, and here's y of t, that's y2, that's where I store that. Y4, that was y prime, I don't care about that now. Let me go back here, and let me zoom fit this thing between 0 and 18, so zoom 0. I've already got 0 and 18 plugged in my window. And they're telling us there's exactly 2 times between 0 and 18 where we hit 0 for the y value, which is good because, I mean, if you look at this, it's not really clear if we're crossing once or twice, but if there's only 2 times, then that means we must be touching once here and once here. Great. Let's find those 2 times. And when I find them, so let me set up this on the paper here. So I did y of t equals 0. When I find these 2 times, I am going to call them E and F, so I don't have to rewrite those crazy decimals, whatever they are. So let me do second trace zeros, and my left bound, let me roller coaster over here to the left. So we've got this spot here, we've got a little bit to the right over here, and press enter again, giving us 6.2832. I guess you could just make it 6.283 and round it off. I'm going to call that, so there's my roller coaster height. I'm going to call that E, and that's in seconds. And I'm not actually going to bother storing it on my calculator because I don't actually need to evaluate anything. I just need to set up an expression for the average speed. So let me just go back to the calculator now without even bothering to store that. And let me just find, let's see, second trace. Let me find my other 0 for this. So move a little bit forward here, and we press enter around here. Whee! Enter one more time, and we get about 12.5664, which I will refer to herever after as F, and that's in seconds. At this point, we need an expression for average speed. So that's going to be 1 over the interval length. So I'm going to call this 1 over f minus e times the integral from e to f. This is why I set up these letters, so I don't want to have to keep writing those numbers there. And now what am I putting inside? Well, if I want the average speed, I need to put the thing I'm averaging inside. So I need an expression for speed. That's going to be the square root of x prime of t squared plus y prime of t squared dt, like so. And the good news is x prime and y prime are already defined up here, so I don't need to bother rewriting them. So this is good. Just one more thing. We wanted average speed in meters per second. So just to be on the safe side, I'm going to stick units after here, and that should do it. For this calculator-based free response problem, we have a particle going along a curve in the xy plane. That's usually how it starts. Here's our position, x of t, y of t, and our velocity vector is given down here. At time 1, our particle's at 3, 5. For part A, we want the x-coordinate of the position of our particle at time 2. So I'm going to start for all of this by spelling out that x prime of t equals cosine of t squared, and y prime of t equals e to the 0.5t. I probably don't need to do that. That's probably understood, but I mean, it doesn't cost me much, and now I'm really sure that when I write x prime and y prime, people know what I'm talking about. All right, so now to the problem at hand. If we want the x-coordinate at time 2, we need to use our fundamental theorem. So we're going to say x of 2 equals the value at time 1, which was 3 for the x value, plus the integral from 2, or actually integral from 1 to 2 of, now I can just write x prime of t dt, and leave it to my calculator. Now, one thing I am going to do first on the calculator is enter x prime and y prime as y1 and y2 in the y equals, so I can use them quickly. And now, quitting out of that, I've got 3 plus math 9. Let's see, not 9, I need math 9. Math 9, there we go. Integral from 1 to 2 of, and I'm doing x prime, so that's going to be my y1 that I just stored, so alpha trace y1. Dx comes out to a grand total of about 2.557. No units on this problem, so we're just going to leave it at that. For this problem part, they're telling us between 0 and 1, there is a point on the curve where the line tangent to the curve has a slope of 2. What time is that happening at? So we need to write an expression for the slope of the curve, which, since this is a parametric function, we can say dy over dx equals y prime of t over x prime of t. So there's our general formula for our derivative here. Although we've defined x prime and y prime, so this is actually a specific function now in the problem since I spelled out what those are. And we want to know where this equals exactly 2. So let's find this on the calculator. To make this happen, I need to enter this function in my y equals. I'm going to define this in y3. So I'm going to do fancy fraction here. We've got y prime, which is, let's see, alpha trace y2 over x prime, that was y1. So that's my derivative, that's my slope. Now I need to see where this equals 2. So I need to actually graph the line y equals 2 and see where that intersects. I also need to unselect my derivatives from before because I don't really want to graph those. I just want to graph these other two things. Now for my window, they said this happens on the interval from 0 to 1. So let me go to window and do 0 to 1 and hope for the best on this. Zoom fit, zoom 0. Let's see if we can see that intersection. They didn't include 0 and 1, so I guess I could always leave those out if I needed to. So here is my slope. Here's the line y equals 2. Let's do now second trace option 5 for intersect, and I'll just press enter, enter, enter. There's only one intersection, and that happens at about 0.8402. So there it is. There it is. And they didn't have any units, so that's the time. Hey, we're done. For this problem part, we want to know at what time the speed of the particle is 3. So we need to set up an expression for speed and then set it equal to 3 and solve that on the calculator. Okay, so speed is going to be the square root of x prime of t squared plus y prime of t squared. And again, we've spelled out what x prime and y prime are, so we can write this, and now they know exactly what we're talking about. and we want to know where this equals 3. So back to the calculator we go. So I'm going to define another function, and before I do that, let me actually deselect y3 and y4 because that was my slope and my y equals 2 that I no longer care about. Let me put my speed function now in y5. So this is going to be, let's see, square root of, and now I need, this is going to be y1 squared because that's where, again, I have x prime. So alpha trace y1 and square that, plus, now I do alpha trace y2 and square that. So there is my speed function. I also need to graph the line y equals 3. And I'm hoping that, well, let's see, they didn't say it was on the interval from 0 to 1. So, I mean, let me zoom fit this and see if it actually works on the interval from 0 to 1. But I'm skeptical that we're actually going to see what we want to see on here. So there's our speed function, ironically going very slowly. And hopefully we see a horizontal line. Oh, it's all the way up there. All right, so this is not going to happen on the interval from 0 to 1. We need to go a little further out. How far out? I'm not really sure. So let me go from 0 to 10. I mean, why would they make an answer on an AP test greater than 10, right? Let's zoom fit this and graph that speed all over again. So here's our speed function. Now the problem here is this is involving other functions as well. And now it looks like we can barely see that intersection, but we can see it. So let me do second trace, intersect, enter, enter, enter. It'll find it. It's down there at about 2.196 if we round off. So there it is if you zoomed in a little bit more, and we're going to call it a day on that one. For this last problem part, they want us to find the total distance traveled by our particle from time 0 to 1. So we're going to have to integrate the speed of the particle from 0 to 1. So we need an integral from 0 to 1 of square root of x prime of t squared plus y prime of t squared dt. Now the good news, doing this on the calculator, we actually entered this speed expression here as y5 on our calculator when we were figuring out when it equaled 3. So it's going to be a lot faster now to enter all this on the calculator. So back on my calculator then, let me do math 9 to get my integral. We got 0 to 1. And in here, this whole thing is just, let's see, alpha trace. This is y5. That's where we stored that. Put a dx. And this is all coming out to about 1.595. For this calculator-based free response problem, we have a particle going along the xy plane. X of t, y of t are the components of that. And they're giving us the derivatives of that. So these are the components of velocity here, x prime and y prime. They're telling us at time 3 our particle is at the point 5, 4, so that'll be useful at some point. And we want to find the speed in part A, find the speed of the particle at time 3. Well, for speed, you basically need to take your velocity components, plug in 3, square those, add them together, and square root it. So basically Pythagorean theorem of all that. So we have square root of x prime of 3 squared plus y prime of 3 squared. All of that being square rooted now, and these things added together. So we're just going to do this on the calculator. So on my calculator, to make things a little more convenient, I've entered x prime and y prime as y1 and y2 respectively in the y equals. Quitting out of there now, I just need the square root of, let's see, we need y prime or x prime of 3. So that's going to be alpha trace y1. Let's plug 3 in there. And now let's square that. Plus alpha trace y2. Plug 3 into that and square that one as well. And press enter. Speed is about 1.011. No units, so they don't get any units back, and we move on to the next part of the problem. For this part of the problem, they want the equation of the line tangent to the path at time 3. So for tangent lines, we need an x, a y, and a slope. Well, they gave us the x and the y here. They said at time 3, we're at the point 5, 4. So we don't have to find those. We do still need to find dy over dx at time 3, though. To do that, using our parametric slope setup, we use y prime of 3 over x prime of 3. So let's do that on the calculator. So that's going to look like y2, because that's where I stored y prime of 3, over y1, where I stored x prime of 3. And pressing enter, it's about negative 0.149. So there's our slope. Putting it all in point slope now to get a tangent line, we have y minus the y value of 4 equals the slope we just found of negative 0.149 times x minus the x value of 5. And that's it. We didn't have to do anything else there. For this problem, I need to know if there's a time at which my particle is farthest to the right, and I have to justify all of this and give the x-coordinate of that position of the particle if this is the case. So let me start. Since I want to, we basically want to maximize the x value. Farthest to the right means it's as positive as possible. So that means we need to find critical values for x prime of t. So let me set x prime equal to 0 and solve that on the calculator. To do this in my calculator, I'm in my y equals here. Notice that I've deselected y2 because I don't want to graph y prime, just x prime. And for my window, they didn't really tell me much other than time being positive. So let me zoom 6 this thing, and we'll see if we cross the x-axis anywhere. So we do definitely cross right about here. It looks like a value of 2, but appearances can be deceiving. Let me second trace option 2 this thing to get zeros. And let me just make sure that's really the x value 2 there and not something else. And I guess it'd actually be a t value, but it says x here. So yeah, it is 2. So this happens at t equals 2. Now, this by itself, even drawing a little picture here, this doesn't prove anything. To actually justify that this is the furthest to the right, we have to say, let's see here, x prime of t is positive, greater than 0 on the interval from 0 to 2. So basically, we're increasing the x value until we get to 2, and x prime of t is negative after that. So for t greater than 2, therefore, our max value occurs at t equals 2. X is absolute max value, which means we're furthest to the right. And that means essentially that, yes, there is a furthest to the right point, time, which answers their question. Okay, we're not quite there yet, though. We need to do the x-coordinate now at that time. So I'm going to need the fundamental theorem here. I'm going to say that x of 2 time 2 equals my initial x value of 5 plus, now I'm going from time 3 to, let's see here, this is time 2. So integral from 3 to 2 of x prime of t dt. And let me just do all that on the calculator. So here's what I entered. We have 5 plus integral from 3 to 2. y1 again was where we stored x prime dx. And press enter. That's going to give us an x value of 5.792. For this last part of the problem, they want us to describe the behavior of the path of the particle as t increases without bound. So we basically need to take the limit as t approaches infinity of, well, each of these motion derivatives here. So let me do the dx of dt1 first. So we're doing x prime of t now. If I do that, as t approaches infinity, this 6 over t term is going to 0. So this ends up just being negative 3 to the 1/3 power, or negative cube root of 3. In general, that's a negative number. So if we have a negative slope as t approaches infinity, that means, and this is happening on the x prime, that means we are moving left as t increases without bound, as time increases. Now we have to figure out the limit as t approaches infinity of y prime of t. So to do that, I'm basically finding the limit of t over e to the t. So I'm going to rewrite this here. And this is a bottom-heavy function. Exponential growth is way faster than linear growth. So this whole thing is going to 0. If your y values are, or your change in y is approaching 0, that means that you're going neither up nor down in the long run, which means you're approaching a horizontal asymptote as t approaches infinity. So overall then, we're moving left toward a horizontal asymptote.